You are welcome to the Zoom session of the course unit of Business Mathematics. Today we will be conducting with the fifth session. Very, very important topic, set theory. So, in today's session, we will discuss the key concept and work through examples to help you understand the application of set theory in business mathematics. So, this theory, set theory is essential in management and business for structuring, optimizing, and analyzing data. So, it also facilitates through Venn diagram, identifying intersections between operations such as overlapping marketing channels, so overlapping customer demographics, enhancing efficiency, right? So this is the practical situation we can apply this theory. And so also the set theory can assist in decision making by categorizing options into different set based on their attributes, allowing for a systematic evaluation of alternatives. So then in this session, we will learn basic things comes under this theory. Basically definition of the set theory, definition of set and set notation, and the way of describing the sets and Venn diagram, and finally we can understand how to solve practical problems by using set theory and set theory's concepts. So now we will move to the session. First, introduction of set theory.
What is the set? Now, generally we can say sets are represented as a collection of well-defined objects or elements. And also it does not change from person to person. Therefore, we can say a set is represented by a whole, it represented as a whole of well-defined objects. And generally set is notation, or set theory is represented by a capital letter. The number of elements in the finite set is normally known as a cardinal number of set. Okay, so likewise we can explain about or regarding the set theory further. In set theory, coming parts, right? Next part, you will learn, or you can learn about sets and its properties, and because it was developed to describe the collection of objects. So you have already know basic mathematics, right? Basic mathematics in mathematics rules. So sometimes we have to apply those basic mathematics rules when we learn in the set theory. So regarding, so the in mathematics, right? In mathematics, sets in mathematics. So very simply, we can say a collection of objects from a group. And a set can have any group of items, be it a collection of numbers. As example, days of week, type of vehicles, so on. So every item in the set is called an element of the set. And curly brackets are used while writing a set. A very simple example of set would be like this. I'll show you. Set A equal to, these are the brackets, open brackets, and this is example. And there are various notations to represent element of a set. Then usually, or sets are usually represented using roster form or set builder form, or we can represent it statement form, right? So shall we look one by one? Okay. Yes. Maybe I'll show you it. First method. We can represent the set as a form of builder form, right? Builder form. So builder form, right? So builder form means what? The set builder notation has a certain rule or a statement that specifically describes the common features of all the elements of a set. Then the set builder form uses a vertical bar in its representation with the text describing the characters of the elements of the set. For example, set A equal to, we can write in here K, and K is an even numbers. Even numbers. Then put in bracket, again we can say K also less than or equal to 20. Right? So this statement says all the elements of set A are even numbers that are less than or equal to 20. Right? So sometimes, so the most of time, right? Most of time we use this method represent our set. So, and another example, right? We can write in generally set A equal X. What is the X? Property, right? Property. So we can close the bracket. And in builder form always describe what are the elements, the command generally describe it, what are the required or relevant, what are the relevant things, right? What are the relevant things in the relevant elements? What are the relevant elements? Should be include the described or presented set. So one more example I would like to show you. So we can write A, set A equal to X. Then again X equal to 2n, and n is element, sample element is the element of n, and again we can write 1 greater than or equal n less than or 4. Then all the descriptions, right, relevant to the required about the set, we can represent there, right? And next method, or the another roster form, right? Roster form is another method we can represent our defined set. So this is the most common form used to represent set. That is the roster notation or roster form. Right? We'll write here roster form or roster notation. In this roster notation, in which the element of the set are enclosed in curly brackets separated by commas. For example, shall I get it set B name? Set B equal to 2, 4, 6, 8, 10, which is the collection of the first even numbers. In roster form, the order of the element of the set does not matter. For example, the set of the first even numbers can also be defined as B equal 2, 8, 4, 6, 10, no order, right? So also if there is an endless list of elements in a set, then they are defined using the series of dots at the end of the last element. We can put the dot. Where x is the set of natural numbers, so then we can represent that set as this way, right? 1, 2, 3, 4, then we can put the dots. But if our set is the first 4 natural numbers, then no need to put this dot. Then this is our set. So remember, in roster form, all the elements of a set are listed, right? So then this is that's why we say this method is most of the time we use represent our set. And next method that we can use, or that we can use to represent our set is so just roster form already we understood, and builder form you know, and the next method is statement form. Statement form. So in statement form, the well-defined description of a member of set or element of set are written and includes the curly brackets. For example, the set of even numbers less than 15. Then in the statement form, it can be written as when I put in here, C equal to even numbers less than 15. So that is the example for statement form. The statement notation described by statement to show what are the elements of a set. Okay, so that is another method. So however, you have to know how to are not how to represent the set, required set by using the different notations or different method, right? Because most popular 3 different methods that we can use to represent sets are set builder form, roster form, and a statement form. So, and also now you know the different among these 3 methods, right? And next, when I move to your lecture note, yes. So next we can we have to understand different type of sets, different type of sets. We have several or more type of sets in mathematics. There are empty set, finite and infinite sets, proper set, equal set, etc. Right? So let's see one by one. Empty set, right? We say empty set. Empty set. So a set which does not contain any element. A set which does not contain any elements is called an empty set. Or sometimes we call that type of test null set, right? So how we denoted by that? We use empty brackets like this way, or we use this notation also to represent the empty set. So the set of a set we can represent by using these 2 brackets. So this notation to represent the empty set. And finite set, right? Finite set, or yes, finite set. That's another type of set. A set which contains of a definite number of elements called a finite set. Example, a set of natural numbers up to 10, that is finite set. We can write it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So what is the opposite of that infinite set? So infinite set means a set which is not finite is called an infinite set. So example, a set of natural numbers. So no end. So we can write set of natural numbers 1, 2, 3, 4, 5. Then we can put the dot like, right? So this is the sample of infinite set. And another type of set is equivalent set. Equivalent, right? Equivalent set. What is the equivalent set? If the numbers of elements is the same for 2 different sets, very clear. If the number of elements in the same for 2 different sets, then they are called equivalent sets. So the order of set does not matter here, right? Remember, and it is represented as NA equal NB. That means A and B sets are equal. Again, so example, we can write it this way: A equals 1, 2, 3, 4, and also B equal maybe this way 4, 3, 1, 2, right? No, need to follow the order. So, however, or we can say A equal B. That is the way how we represent or show the how we can show equal sets. And next type of set is disjoint set. Disjoint set. The two sets, if you call the A and B, are the two sets A and B are said to be disjoint set if the set does not contain any common element. So, example, set if the set A equal to 1, 2, 3, 4, and if B equal to 5, 6, 7, 8, right? These two sets are disjoint because there are no common elements between them. And there are more bit higher thing, little bit advanced things, right? We have to learn. So just I will explain this, and later again we will I will explain these things when we are doing sets operations, right? Until just get the knowledge you can regarding this one. One is the subset, right? Subset. Sorry. Subset. Subset. How we can define that? A set A, right? A set A is said to be a subset of B if every element of A is also an element of B. This is denoted by or denoted as A subset of B. Or we can write A subset of B. Even the nuts, even the empty or null set is considered to be a subset of another set. In general, a subset is a part of another set. Example, if A equal 1, 2, 3, 3, and B equal 1, 2, 3, 4, 6, 7 likewise, then we can say A is subset of B. A is subset of B. So, note that the set is also subset of itself, right? And a set is not a subset of another set, then we can denote it this way, right? When using this one. So, as an example, if the A is not a subset of B, then it denoted as A not a subset of B. And further, union of sets, right? That is another important thing. Union, U-N-I-O-N, okay? Union of set, or we use universal set word, similar both are universal set, right? So union of set, what is the union of set? If set A and set B are two sets, then A union B is the set that contains all the elements of set A and set B. And also we know the notation, or it is denoted as A union B. An example, A union B. An example, if set A equal to 1, 2, 3, and if set B equal to 4, 5, 6, then union of A union B, okay, A union B equal to 1, 2, 3, 4, 5, 6, right? And another thing is as that we know now, union or universal sets is similar. Set which contain all the set relevant to the certain condition is called the universal set or union set. So it is the set of all possible values, right? So this one also we can, when we represent in this one, just think here, right? Set A has more values like this one, 4 and 5, right? And then set B is this one. So again, our union of set is this one, right? No need to put the same element twice because this one is here, this one is here, 4 here, 4 here. But in our set of union, we are not to put the twice the same one. Just it is you have to put the one time, right? And further. We understood these things, right? Empty set, zero set, right? Or the symbol, yeah? This is the element, this symbol, right? This symbol, right? We used to say that the object is a member of a set, element of the set, right? It has a partner symbol, right? So we can refer it as an element also, right? We use to say this notation or symbol. We used to say that the object is a member of a set, and it also we used to used to refer it as an element also of the set, right? And next we understood universal set, equal set, right? Subset, and union of set we did, yes. Then in intersection, right? So these things we can understand also under the subtopic of operations of set, right? However, just already now we know the symbol, this symbol, right, is employed to denote the union of two sets. We understood, right? So normally we read it A union B, or the union of A and B. And it also defined as the set that consists of all elements belong to either set A or set B, both, right? And now we move to the intersection, right? So the intersection, yes, intersection, this is the notation. The intersection operation is denoted by the this symbol, by using this symbol. So set A intersection B, right? We read that one, A intersection B, or the intersection of A and B, right? So is defined as the set composed of all elements that belong to both A and B, right? Both A and B. So In this example, you can go through in here, the symbol used to show the intersection, this one. So then as an example, S intersection T. S intersection T, right? That means here X belong to SO, X is an element of SO, X is an element of X. So I will explain you one more example. Right? If our set A, right? Set A equal to 2, 4, 6, 8, and set B equal to 4, 10, 16, right? Then A intersection B equal to only 4, right? Because these are the common elements for the both sets. And one more thing, you have to know complement. Yes, shall I move to the next one? Next slide. Yes, complement of set. So set, let A be a subset of the universal set. Then the complement of A with respect to universal set is the set of all elements of universal set which are not in A, and it is denoted by A dash O. We use to show the complement of set A dash O, A complement. See, like here, see. Okay. But remember, the always complement of set depends on which universal set is chosen. Right? Based on the universal set, we define our complement, set of complement. So if our Venn diagram, we can show it Venn diagram. No, I'll move to later for the Venn diagram. So anyway, if our universal set is 1, 2, 3, 4, 5, 6, 7, and 8, right? And if A is 1, 2, 3, 4, okay, then complement of A or complement of, we can use both notation, that set equal to only 5, 6, 7, 8, right? Those elements we have taken from our universal set. That's why we say complement of set always depend on the universal sets that we chosen or that we select. Right? And next, yes, Venn diagram. Right? This is the most important thing, or most important section in this set theory. Venn diagrams are a useful way of visualizing relationship between sets. When we draw Venn diagrams, sets are represented by circles. The inside of the circle represent all the elements that are members of the set, and the outside the circle represent all the elements which are not members of the set, which are not element of the set. And also the area where circles overlap represent set of elements which are in all of the sets corresponding to the overlapping circle. So we call this area in intersection of the set. And one more thing. The sample space is represented by a rectangle, which is drawn around all the circle, and we write the set name of the sample space. And if we want to partition the sample set into the multiple parts, we draw lines to divide the rectangle into the required number of parts. So, however, I will show you, right? I will show you. Yes, I will show you how we represent the each notation. So each type of sets with through the Venn diagram. So, however, in as the again, right, I will remind in Venn diagram is a pictorial representation of set, which each set represents as a circle, right? So, element of set are presented inside the circle, right? Sometimes rectangle enclose the circle, which represent the universal set. So, anyway, Venn diagram represent how the given sets are real operations on sets. So, in set theory, yes, shall I explain this one? Now you can say in here, union, right? Two sets union we can represent with the Venn diagram this way, right? So you can see the rectangle here. In this rectangle we use to denote our union, union, right? And this A is our one set, B is another set, and the union is colored area. Yes, right? That means this is the A union B area for relevant to the A union B. And same time, right? Same time we can present this intersection. Same way we can represent the intersection through the Venn diagram this way, right? You can see A intersection B is both the part which is relevant to the both sets. And yes, complement, right? Complement of set, right? So you can see if our set is, or considering set is A, then complement of it's equal to this colored area, right? You can see colored area is here, this part, right? This is the colored area. And yes, before move to the summary, I need to explain some more things for you. So, in set theory, the operations of the set are carried when two or more sets combine to form a single set under some of the given conditions. The basic operations of set are unions of set, intersection of set, complement of set, Cartesian product of set, in set theory, the operations of the sets are carried when two or more sets combine to form a single set under some of given conditions. The basic operations on sets are union of sets, intersection of sets, complement of a set, Cartesian product of a set, and set differences. Basically, we know basically more on union and intersection of set operations, and we can do those things using Venn diagram also. And this intersection of sets and complement of sets already we understood in this session. So when we consider in the Cartesian product of sets, Cartesian product of sets, if set A and set B, when we consider in set A and B, if set A and B are two sets, then the Cartesian product of set A and set B is set of all ordered pairs such that is an element of A and B is an element of B. So it is denoted by A multiplied by B. So we can represent it in set builder form. We already know how to do the set builder form. So we can represent it in set builder form such as A multiplied by B equal, we can put in, open the bracket, A and B. This A meaning A is object of A and B is also object of B, capital B set, right? So, and also that example we can type this way, set A equal 1, 2, 3, and shall we assume our set B as set B, I put here one object is bat, other object is ball, two objects, right? Bat and ball. Then A multiplied by B. Okay, I'll write here. Okay, then A multiplied by B. Right? A multiplied by B is 1, right? For set A1 and bat. Okay, bat from set B, right? Then another object can be A1 and ball, right? Ball. And same as another object we can take from the set A2 and bat. And one more can be a 2 and also ball, right? And when we consider in the last object of the set A3, then 3 and bat can be 1, right? And also 3 and ball. Okay, so that means that if we consider the set A as set A's elements are 1, 2, and 3, and set, if we suppose set B's elements are bat and ball, then set A multiplied by set B equal to this one. Okay, so that's the Cartesian product of sets, right? And also another important thing is difference of set. So if set A and set B are two sets, then set A difference, set B is a set which has element of A but no elements of B. it is denoted by as A minus B. Okay. So as an example, right? If A equal 1, 2, 3, and if B equal 2, 3, 4, right? Then A minus B set is equal to what? When we minusing 2 into it, remove 4. And A minus B equal to only 1. Okay. And so anyway, there are some formulas, right? Most important set formulas that we can use to solve our problems relevant to the set. Okay. So what are those theory formulas? First, N A union B, right? Number of elements in A union B. It should be equal to NA, number of objects or elements in set A, plus number of elements in set B, minus number of elements in A intersection B. That's how it becomes. So we know when we use in the Venn diagram, you can see if this is set A and this is set B, so A, B. Okay? So then A union B is equal to this part, and this part. Okay? A, B, and intersection part. So when we add in, so N A union B therefore equal to when we add N A, when we add in N A mean what is the section, that means this whole part. Okay. And then when we next add in NB, that means we can we again add this part. Okay, this part, right? Then what has happened? So this middle part, that means intersection part, we add twice. Earlier when we add in A, and now we when adding B, then both times, 2 times we add the intersection section. Therefore, we have to reduce or deduct A intersection B, right? Then it equal to the A union B, right? NA union B. So that is a very, very important formula in the set section. And one more formula is if A intersection B, right? Intersection B equal to 0 set. Then what has happened? N A union B equal to NA plus NB. Right? That means no intersection section. Right? Then when we using when we represent this situation in Venn diagram, our A and B should be this way. A, B, right? No intersection, because if intersect, when supposing intersection path is 0, right? Then our N A union B should be equal to NA plus NB. Right? So this part and this part. That's the another one. And another one is when we deduct P, right? So N A minus B, when we deducting B from N set A plus N A intersection B always equal to NA. Okay, it's very clear. All right. When we deducting B from, when we deducting B, set B from A, and when we add in A intersection B. It's also clear, no? Right? When we put in our A and B this way, right? A minus B then equal to A minus B at this intersection part equal to this A. Okay, it is also clear. And it's also, you can understand with opposite way, that means in B minus A, then it's also should be, then in B minus A equal, in B minus A plus n times, so A intersection B, then it equal to B, similar to the earlier one. And another thing is, yes, if we have A, B, C, like 3 sets, right? So then A in A union B union C, right? In A union B union C, it should always equal to NA plus NB plus NC. And we have to deduct in here N A intersection B once, and again in B intersection C, and minus in C intersection A, and then we have to add finally N intersection B intersection and C intersection. Okay, so that is another formula, important formula. So anyway, you have to keep in your mind set symbols always, right? Already we discussed, but as a summary, right? As a summary, I would like to just remind it again. Shall I write all the, yes, this one, right? You can see this is union, right? Union, and this is intersection, right? Intersect, that is the symbol. And proper subset, we use this one for shows the subset. And not a proper subset, then we use this notation. And super subset, you use another notation like this. And this notation we use to show the is a member or element, right, of the set. And when we use this one, it is not a member. It represents that one number is not the element, is not a member of the given considered set. Right? In addition to that, when we write in this one, that means, shall I take this slide? Okay. So in addition to that, when we write B, right, object A, right, element, that means B is an element of set A. Okay, and also we can write this way. Okay, that means A is not an element of set B, right? So, and also we use these brackets to denote the set, and this one we use to show the null or empty set. And all we discuss this one more times. A union B, set A union set B, and set A intersection set B, and A set A is a subset of set B, and B set B is the super subset of set A. Okay, so and also there are some properties, right? Properties of set, that means similar to numbers. Set also have properties like associative property, commutative property, so on. So there are important properties of set. So we can discuss it, right? supposing if we have three sets A, B, and name, when we name in three sets A, B, C. Suppose we have set A, set B, and set C. Then based on that, we can explain, right? Discuss properties of these sets, properties of these identified set. That means if we have set A, right? Set A, set B, and set C, three sets, right? So according to the commutative property, A in union B always equal to B union A, and also A intersection B equal to B intersection C. Sorry, B intersection A, right? So when we consider in A and B, and also when we consider in three A, B, C sets, so it's we can explain according to the property of associative. Then we can say A intersection B and A intersection B intersection Z equal to A intersection B intersection of C, right? So same thing we can here something. Yes, I will write it again. Yes, A intersection. Yeah, so right, no, B intersection C, and for that one we can explain as for the union. So okay, that means the associative property. According to the associative property, if we have three sets A, B, and C, then we can say A union B union C. This one always equal to A union B union C, right? And according to the distributive property theory or distributive property, again we can write A union B intersection C equal to A union B and intersection A union C, right? So these things we can further understand with the Venn diagram. Okay, you can see then if we have, right, A, B, C, three set line. So A union B, if I put here A, B, C, then you can see A union B is this part, right? A union B, right? A union C again, I use another color. A union C equal this part, okay? Then you can see A union B intersection A union C. That means the color twice, the area which I colored twice, right? So then you can see what is the twice colored area. This part and this part, okay? Then it is also equal to B intersection C, that part, and union of A, right? Whole A and B intersection C. You can understand that one, okay? So also according to this property, distributive property, we can write A intersection B union C equal to A intersection B union N A intersection C. Okay, this one also you can understand with the or we can explain it through the Venn diagram. Right? This is A, this B, and C. Okay, then first we have to show in our Venn diagram part which is inside the bracket. B, just I will do this part, right? Then you can understand very clearly. A intersection B, right? What is the A intersection B? This part, okay? And A intersection C. What's the A intersection C? This part, okay? Then what is the A intersection B union A intersection C? That means this whole part, okay? Same thing we can do another graph with another chart A, B, C, and considering the other side. B union A, right? What is the B union A? B union A is this part, okay? And what is the A? Right? What is the A? I colored A. This is the A, okay? This is the A. What we need? A and A intersection with B union C, right? B union C intersection, right? That means again which area that I colored twice. Okay, you can see this area. Okay, then it is very clear. It is equal to this one, right? That's why we say these two parts. We confirm, right? We can justify. It's okay. These two parts is equal. And one more property is identity property, right? According to the identity property, A union 0 set equal to A. And also A intersection union, union, it's equal to A. And complement property, according to complement property, A union complement of A always equal to the universal set, right? And yes, those things you have to know as the properties of sets, right? And in addition to that, right? So I think you should have to get the clear knowledge how to present all these things with the Venn diagram. So just one thing I want to say, right? These things already we know, but you can see if we have two sets A and B, right? You can say this is the set A. Likewise, other side, this other part is the set B. This is the set B. This is the set B. Okay. Why my pen is not working? Yes, this is the set B. And also, is the union, we know, a universal set, and A, B. Right? This is A, this is B. And what is the complement of A? Complement of A means all these parts except A, right? In this part, right? That's the complement A. We use this one or this notation to show that complement A, right? So then similar to that one, then what is the, when I put A, B this way, what is the then complement of B? Complement of B is this, complement of B. That means B dash or B complement. Okay. And A and B disjoint sets. If A and B are disjoint sets, then remember when there is no intersection, then you have to show your two AB sets like this. Okay, that means A and B are disjoint sets. And if your B is a subset of A, then how you can represent that in your Venn diagram? Okay, the big one is B, then right B. Sorry, big one is A because B is the subset of A. Then big one is A. Then this small one B. B is subset of A. So you have to represent this one is there. That means we can say B is proper subset of A. Okay. So and you already know A and A intersection B, right? That means A intersection is this one and A union B is whole. Okay. So I think those things you have to understand now. In addition to that, in this session, there is no enough time to discuss those things. But I think better if you practice, right? Better if you can practice some sections, right? Set sections. How to represent or how to how to show given information through Venn diagram. And if you have some information and when it asks in the what is the probability of something is happening, right? Likewise, so those things, the questions, right? Questions like this type questions, you need to practice. So I think some example questions are in your LMS page, right? And some questions already, answers for some questions are already, they are given, and then you can practice it. You can check first you can do those answer those questions, and then you can check whether your answers are correct or wrong with the result, with the feedback already given in the LMS page. Okay, so then this session also I finished this session now. So I think we can meet again with another topic. Thank you very much.